Have you ever wondered where it all began? The story of our universe is one of the most fascinating tales ever told. I mean, everything, the universe, the stars, even us. How did it all come to be? What sparked the creation of everything we know and see around us? Well, buckle up, because we're about to embark on a cosmic journey that started roughly 13.8 billion years ago with the Big Bang. This monumental event marks the birth of our universe. Imagine a universe smaller than an atom, incredibly hot and dense. In this tiny, almost inconceivably small space, all the matter and energy of the universe were packed together. Suddenly, it began expanding rapidly, an event we call the Big Bang. This expansion was not just a simple explosion, but a rapid stretching of space itself. This wasn't your typical explosion like a firework. It was far more profound and complex. Instead, it was the expansion of space itself. Space didn't just contain the universe, it was the universe, and it was growing. And it's still expanding today. The galaxies are moving away from each other, and the universe continues to grow larger and larger. The Big Bang Theory is currently the best explanation we have for the origin of our universe, supported by a wealth of scientific evidence. From the cosmic microwave background radiation to the abundance of light elements, the clues all point to this incredible beginning. Scientists have spent decades piecing together this cosmic puzzle, using advanced technology and innovative methods to understand our universe's origins. The journey of discovery continues, as we strive to learn more about the cosmos and our place within it. Now, let's talk about cosmic inflation. In the first fraction of a second after the Big Bang, we're talking a tiny fraction, like 10 to the power of negative 36 seconds, the universe expanded exponentially. This period of rapid expansion is known as cosmic inflation. Imagine a tiny balloon suddenly inflating to the size of a football field. That's cosmic inflation. This dramatic event helped smooth out the early universe, explaining why it looks remarkably similar in all directions today. Without cosmic inflation, the universe would have been a much messier place, with large temperature variations and an uneven distribution of matter. As the universe cooled down after inflation, energy started converting into particles, following Einstein's famous equation E equals mc squared. It's like cooling a pot of boiling water. As it cools, steam condenses into water droplets. In the early universe, energy condensed into fundamental particles like quarks, electrons, and neutrinos. These particles were zipping around at incredible speeds, colliding with each other in a chaotic soup. But as the universe continued to cool, these particles started to slow down and interact with each other, setting the stage for the formation of atoms. Around 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to combine, a process called nuclear fusion. This led to the formation of the first atomic nuclei, primarily hydrogen and helium, the two lightest elements in the universe. This period is known as Big Bang nucleosynthesis. Think of it like baking a cake. You need the right temperature and ingredients for the cake to bake properly. Similarly, the early universe needed the right conditions of temperature and density for nuclear fusion to occur and create these light elements. Section 5. Let there be light. The cosmic microwave background. For the next 380,000 years, the universe was a hot, opaque soup of atomic nuclei and free electrons, a chaotic and dense environment where light couldn't travel far without being scattered or absorbed. This period is often referred to as the cosmic dark ages because the universe was essentially opaque to radiation. During this time, photons, or particles of light, were constantly interacting with the free electrons, making it impossible for light to travel freely. The universe was a seething, turbulent place, with energy and matter in a constant state of flux. However, as the universe expanded and cooled, the energy levels dropped, allowing the environment to change dramatically. Electrons began to combine with nuclei to form neutral atoms, primarily hydrogen. This event, known as recombination, marked a significant turning point in the history of the universe. With the formation of neutral atoms, the universe became transparent, allowing light to travel freely for the first time. This transition from an opaque to a transparent universe was monumental. This first light, which has been traveling through the universe ever since, is a relic of that early time. It carries with it the imprints of the conditions that existed in the universe at that moment. Today, this ancient light is detectable as the cosmic microwave background, or CMB. The CMB is a faint glow that fills the universe, providing a snapshot of the universe when it was just a few 100,000 years old. Imagine a faint afterglow of the Big Bang, a remnant of the intense energy that filled the early universe. This afterglow is like a cosmic fingerprint, offering clues about the universe's origins and its subsequent evolution. The CMB is essentially a snapshot of the early universe when it was just 380,000 years old, capturing the conditions and structures that existed at that time. Studying the CMB provides valuable insights into the conditions of the early universe, helping scientists understand the distribution of matter and energy, the formation of galaxies, and the overall structure of the cosmos. The data gathered from the CMB also supports the Big Bang theory, offering compelling evidence for this model of the universe's origin. By analyzing the CMB, scientists can trace back the history of the universe, confirming key aspects of the Big Bang theory and refining our understanding of the cosmos. Section 6. From Darkness to Light, Formation of Stars and Galaxies. After the CMB, the universe entered a period known as the Dark Ages. This era, spanning hundreds of millions of years, was a time of profound stillness and silence. The universe was filled with a sea of neutral hydrogen gas, and there were no luminous sources to light up the vast expanse. Not because it was dark in the traditional sense, but because there were no stars or galaxies to illuminate the cosmos. The universe was a cold, dark place, with only the faint afterglow of the Big Bang providing a whisper of light. However, gravity was hard at work, pulling matter together into denser regions. These regions, known as dark matter halos, began to form the seeds of future galaxies. Over time, the gravitational pull caused these clumps to grow larger and more complex. These clumps of matter eventually became so dense and hot that they ignited nuclear fusion in their cores, giving birth to the first stars. These stars, known as population 3 stars, were composed almost entirely of hydrogen and helium, the simplest and most abundant elements in the universe. These early stars were massive and short-lived, but they played a crucial role in enriching the universe with heavier elements. Through the process of nuclear fusion, they created elements such as carbon, oxygen, and iron, which are essential for the formation of planets and life as we know it. As these stars exploded as supernovae, they scattered these elements into space, seeding the formation of new stars and galaxies. The remnants of these supernovae provided the raw materials for the next generation of stars, leading to the complex and diverse universe we see today. This cycle of starbirth, death, and rebirth continues to shape the cosmos, driving the evolution of galaxies and the creation of new worlds. Section 7. Birth of a Star, Our Sun, Formation of the Solar System. About 4.6 billion years ago, in a relatively quiet corner of the Milky Way galaxy, a giant cloud of gas and dust, known as a nebula, began to collapse under its own gravity. As the cloud contracted, it started to spin faster and faster, forming a spinning disk of material with a protostar at its center, our Sun. Within the disk, dust and gas particles collided and stuck together, gradually forming larger and larger objects. These objects eventually became planets, asteroids, and comets, creating our solar system. Section 8. Life Finds a Way. Origins and Evolution of Life on Earth. Meanwhile, on our young planet Earth, something extraordinary was happening. The conditions were just right for life to emerge. We still don't know exactly how life began, but we know that the first life forms were simple, single-celled microorganisms, probably living in Earth's early oceans. Over billions of years, life on Earth evolved and diversified. From these single-celled organisms arose more complex life forms, eventually leading to the incredible diversity of plants and animals we see today, including us. Section 9. From Single Cells to Civilization, the Epic of Human Evolution. Humans are relative newcomers to the cosmic scene. Our lineage diverged from our ape ancestors around 6 million years ago in Africa. Over millions of years, our ancestors evolved and adapted to their environment, developing bipedalism, larger brains, and complex social structures. From the first tools to the development of language and agriculture, humans have made remarkable progress, eventually establishing civilizations and leaving their mark on the planet. Our journey from the Big Bang to present-day civilization is a testament to the incredible power of cosmic evolution and the interconnectedness of everything in the universe.